We already explored the case study in academic achievement, and we applied a simple linear model with just one parameter, beta 0, to make predictions about the data. And the beta 0 only model is a linear model. You can see that the red line is a line. That's why it's called linear. And we then, you may wonder why I use this transformed or translated the model to the y-axis, when typically what we see the normal distribution in this way. And the reason is that I use graphs are a mean of communication of ideas. And the idea that I wanted to communicate is that academic achievement is the y variable in a more complex model, is the variable that it's the dependent variable, the outcome variable. And so when I add an extra variable, I will have to put it in here, and so the traditional way of representing only one variable would be less intuitive. So let's return to my peculiar way of presenting the normal distribution, because now we are going to the more complex model, in which here we add another parameter, beta 1, and another variable. So the parameter will multiply the values of the variable x, and now the linear model becomes a line that it's has some slope. Now, this data here, the horizontal distribution of the dots doesn't mean anything. It's just a technique that is called jittering, that is used in order to be able to see more of the dots. If we put it one in a straight line, which is what we should probably do if we want to be a purist, because we are using the x-axis in a way that it may reflect that there is a variable here, or there is a difference between a dot being here and there, but there isn't. But the idea is that if we don't do the jittering, there is a lot of overlap, and we don't see the real amount or number of dots in the sample. So that's the idea of the jittering. But when we go to this graph, now the x-axis becomes meaningful. So that belongs to study hours. So I want to show you that this type of graph, this is the scatter plot. It's very common. We observe these when we have two variables, we study regression or correlation, we see these graphs a lot. But this one, we don't. Instead of using this type of graph, there is a bar or a dot representing the mean, and some error bar representing or the standard deviation or the confidence interval or standard error, but we never get the whole data. Why? It's just historical reason. Someone chose not to show the data when we are considering only one variable, and now things are changing, and we consider that it's very important to show all the data. So now I want to say that this is the same number of dots than this, and it's actually the same people. So here we got 300 people with a measurement in academic achievement. Now, this here is a translation of that over the study hours. So, for example, this dot here is the one with the lowest academic achievement. Then that guy is that one in this graph. So it's the one with lowest academic achievement, but in study hours, he or she studied 13, 14 hours. It's not the one with the lowest amount of hours. So the second lowest here, then you translate it, and it's this guy there. Again, not the lowest in amount of study of hours. And the third lowest here, then you translate it, and it is there. Same amount of hours of study. So, and let's take the top one. This one here is the one there. So same people, 300 dots here, 300 dots here, but we make a translation, and now we've got information on how much they score in academic achievement. We knew that here, and now we know how much they score in study hours as well. So this provides more information than this one. Okay, so we are going to use these two models to compare the two models. Before doing that, remember that the beta 1 is the slope of this, the line. So if this line were like there, the slope would be 0 because it's in a diagonal. The slope is given by, for example, at this stage, we go from 0, that it's about 0, to 22.5, and here in y, we go from 35 to around 48. Sorry, no, a bit more than 50 over there. Okay, so what we need to do in order to, what's beta 1? Beta 1 is the units of increase here divided by the units of increase there. And you can do this and in every point of this line, and you do this calculation, it would be exactly the same value. It would be beta 1. Okay, so the more steep the slope, the higher the beta. The less steep the slope, the lower the beta 1 value. Okay? Now, we can redescribe the simpler model of the two. So instead of having a different structure, we can use the same structure as the complex model. So we can call it, same as before, we can say that y is normally distributed with a mean of gamma and standard deviation of sigma, and we say that gamma equals beta 0 plus beta 1 times x, which is the same as here. So it's the same, I just copied this line there. But in this case, we add the following constraint, that beta 1 equals 0. Okay, so if we replace beta 1 with 0, 0 times x is 0, so beta 0 plus 0 is beta 0. So we have the same as before. Why am I doing that? And why am I making it more complex? I just wanted to show that we can show the model here, and we can compare how the two models predict the data. Now visually you can see that basically what we are going to do is some version of this. We are going to compare, we're going to measure the distance between each dot and the line of the model. So when we are considering the model of with one predictor variable, we are going to take the distance between this dot and this line, 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 and all 300 dots we are going to measure the distance. And we are going to do the same with the model with only one parameter, with no predictor variable. So we are going to measure the distance between this dot and that line, 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 and so on and so forth until we do the 300. And we can see that the red line, it's visually we can see that the distance between the dots and the red line will be larger than the distance between the dots and the blue line. So, but we have to do that mathematically in order to compare which of these two models is the best. So we've got two methods. One is called the maximum likelihood method. And basically, remember that we use the model of the normal distribution with mean being beta 0 to make a prediction of each observation, of each of these 300 observations. So, well, we use that normal distribution to make that prediction of each observation. So, for example, values, all these values that are close to this midline, all these values in this distribution are very probable. They have a high probability. But the values that are further away, they have a very small probability. So you, when you start doing this, calculate the probability of each observation in each model, and then you move to the second step, which is obtain the product of those values. You want those products to be the highest value possible. And the problem then is that if then the normal distribution, we know that the mean is the beta is 0, but the standard deviation, we can use different standard deviations that best fit the data. Now, if we do a very small standard deviation, that will increase the probability of the values close to the mean. So that's good. But the values further away from the mean will be less and less and less probable the narrower is the distribution. So when we start multiplying that probability, these values will put down the total value. If we use a very large standard deviation for this distribution, then it will the values at the extremes will be more probable than before, but we lose the high probability we had for the values that are close to the mean. So you have to do this trade-off between capturing the values in the extremes but not losing probability for values in the center. Okay, so basically you have to do that for this the simpler model, and then you do the same for the complex model. Now, the complex model, instead of having one normal distribution, it has infinite numbers of normal distributions with mean. For each x value, the mean is given by the line. Okay, so this is infinite. I'm not showing infinite number of distributions, and I'm just choosing a few of them, but that's the idea. So we are trying to predict the values, and you can see that we don't need a very large, a very spread distribution for each of these to capture most of the values. It's much less spread than this one. And by doing that, you will get when we calculate the product of all these probabilities, it will be lower than the product of the probabilities under the bigger normal distribution. So I recap. We calculate the probability of each observation in each model, and we obtain the product of those values for each model. And then I add here, and we obtain the logarithm. This is because when you deal with probabilities and multiply them, so let's say you got a probability of 0.4, but that you multiply by a probability of 0.01, and then you multiply by 0.001, and so on and so forth. We've got 300. That number is going to be lower, so that when you multiply values lower than 1, the values become lower as you multiply them. So these values are really low numbers that are difficult to deal with a lot of zeros after, with a lot of decimals. So in order to deal with that, we transform this into a logarithm scale that made them more manageable. So that's the only reason. But theoretically, you can do it without adding the logarithm of those numbers. It's just a convenience. Now, the third step is penalize the complex model. Why do we have to penalize the complex model? Well, for something that is called overfitting. Theoretically, here we've got a model. The simpler model has only one parameter, and the complex model has two parameters. Theoretically, I can add as many parameters as observations, so 300 parameters, and by doing that, I can, instead of having a line, I can have a model with a curve that goes over each of the values, and then the prediction will be perfect. So why don't we do that? It's good to have a perfect prediction. Well, not quite, because we are considering that these observations, they come from a model that has some process that has some meaning, and then plus something that is a random occurrence. So we can see that in the error part there is a distribution, or in this version as well, that we've got a standard deviation. So basically we are not making perfect predictions. So there is one random aspect of the model that we don't want to fit the data to that aspect. Why not? Well, what we need to do is to use the models that we have here to try to predict data that is new, not these 300, new data. So let's take observation 301, and we try to predict that observation with one of these models. Okay. Now, if we use the complex model with 300 parameters, the prediction will be really bad. So fitting the data that we have, if we overfit, then we are really bad at predicting new values, whereas the simpler models are better at predicting those values. So that's why you want a model that fits the current data well, but you don't want a complex model. So we have to make this trade-off of how many parameters we use, because the more parameters we have, the better we are going to fit the data, but we don't want to overfit. So we need to penalize for using more parameters. So I'm not going to show you. We use some methods like a Bayesian information criteria or a cake information criterion. Doesn't matter. The idea is that they penalize for using an extra parameter. So you add an extra parameter, so it gives you some penalization, and then you have to add that to this product of values that you had with the logarithm. And then after you do that, you decide which model has the higher likelihood. So which model best explains the data after penalizing for complexity. And in this case, even after the penalization to the complex model, the penalization for adding one parameter is not too bad, because the penalization gets more important the more parameters you add. So the model, the blue with the blue line, is much better.